we are going to look for perfect cubes. We look at the bottom here. Simplest form means that the radical has no perfect nth powers. So it uses that same thing. My recommendation to you guys, look at your root and use that to write out your perfect nth powers. So we have a cube root, so we are going to take each of those standard numbers. We're still going to go 2, 3, 4, 5, but we're not going to square them. We're going to raise them to our root, to the third power. Okay? 2 to the third gives me 8. 3 to the third gives me 27, 64, and 125. So what I'm going to do is I'm going to take 135 and I'm going to divide it by 8, 27, 64, 125. And I'm going to see which one goes into 135 without giving me a decimal. When I do that, I find that 27 is the only one that will go into 135. So what I'm going to do, I'm going to rewrite 135 into 27 times 5. 27 is the only one I can take the cube root out of without getting a decimal. So I do that and pull it out of my cube root. That leaves me with 3 cube root of 5. Like I said, guys, same process. The only problem is, if you look down here, we're going to erase our perfect cubes because we don't need them anymore for this page. If you look down here, we have fifth roots. So again, we're going to start by writing our perfect fifths. Starts with the same numbers, 2, 3, we'll just use 2 and 3. That should be high enough for this one, but you can keep going. Okay? So now our root, our exponent, is going to be to the fifth power. 2 to the fifth is 32. 3 to the fifth, 243. Now, here's the problem. We have a radical in our denominator. Unfortunately, rationalizing and multiplying by that denominator just does not work here. So we would want to try and rewrite things, but we can't do that with 7 or 8. So we're going to use a slightly different technique. We're going to try and turn this denominator into a perfect fifth. So we're going to turn the denominator into a perfect fifth. Okay? The reason we're focusing on the denominator is because we want to get the radical out of the denominator. So you will always focus on the denominator here when you can't simplify it. So if I look at my numbers, I'm going to look at this column and I'm going to say, can I multiply 8 by a number to get me 32? We can. Can I do it for 243? No, we don't want to do that. You want to go for the smallest one here, less work. So we're going to, and remember, it's got to be in that same form according to that product property. So we're going to multiply the top and the bottom by the fifth root of a number in order to turn this into a perfect fifth. Well, we know 8 times 4 is 32. So we're going to multiply the top and the bottom by the fifth root of 4. When I multiply straight across the top, I get the fifth root of 28. When I multiply across the bottom, I do get the fifth root of 32, which, because I was smart and I wrote out my perfect fifths, I know right away that the fifth root of 32 is 2. So there's your answer. When you guys are adding and subtracting like radicals and roots, you're going to treat them like variables. So when you multiply or divide with these radicals, you do actually worry about what's in there. Here we don't. We just want to make sure they match. So for part A, And notice my note here, it says like radicals mean they have the same root. We also call that the index, so they both have to be a fourth root or a fifth root. And the same radicand, the number under the radical. So for part A, we look and they are both fourth root of 10, so we're in business. So we're going to treat it just like a variable. We have 1 fourth root of 10 plus 7 fourth root of 10. 1 plus 7 gives me 8. Fourth root of 10. That's it. It's the same deal with raising it to the 1/5 power. Remember, that's just like saying the fifth root of 8. Okay? So they have the same base, same exponent, so I'm just going to leave it like that. I'm going to treat it like a variable. I'm going to go 2 times my 8 to the 1/5 power plus 10 to the 8. So I'm just going to add 2 plus 10 gives me 12 times 8 to the 1/5 power. And I leave it. We have to get into the mindset of realizing that raising it to a fraction is the same as a radical. So it's okay to leave it like that. Now here, we're going to have to do some rewriting. They do not match. However, 54 is rather big. We're going to see if we can rewrite that into a perfect cube. So I'm going to write my cubes. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. Then I'm going to stop there because I have 54. We know that 27 times 2 gives us 54. And it's almost a clue if we look at that second radical. We want it to match that second radical. So what we're going to do is we're going to rewrite radical 54 into radical 27 times 2 minus radical 2. We can cube root 27, and we wrote out our cubes, so we're awesome. So we get 3 cube root of 2 minus, even though you don't see it, 1 cube root of 2. 3 minus 1 gives me 2. So my final answer, 2 cube root of 2. Treat them just like a variable. You just might have to rewrite to make them match.